This lecture is on chapter 4.5 to 4.10 on naming covalent compounds, Lewis structures, octet rule, resonance, and formal charge. So last class, we introduced the covalent bond and talked about how you could have molecules composed of a series of atoms that are combined by either single, double, or triple bonds. And so now we need to be able to actually name these individual molecules. So to name a binary molecular compound, meaning you just have two different components, you first determine which atom is more quote, cation-like, and which one is more, quote, anion-like, using the electronegativity. So the more cation-like, um, the more cation-like atom name comes first, and the more anion-like name comes second with an IDE ending. So it's going to be similar to our naming convention for our ionic compounds, but they are covalent compounds. So the further they are towards the bottom left corner, the more cation-like they are. The further they are to the upper right-hand corner, the more anion-like they are. Okay, so um, the departure that we have now from the way that the convention for ionic bond or ionic molecule naming, ionic compound naming, is that we include prefixes in covalent molecules in order to indicate the number of each atom that we have. Okay, so our prefixes that we have here are mono for one, di for two, tri for three, tetra for four, penta for five, hexa for six, hepta for seven, octa for eight, nona for nine, and deca for 10. Okay, so when we were naming ionic compounds, there's no different than the naming for NaCl, sodium chloride, or magnesium chloride, which is MgCl2. We didn't call that magnesium dichloride. We didn't include these prefixes to indicate how many of each were there. But for these covalently bonded molecules, we have to include these numerical prefix for telling how much of each atom that we have. So the important note, the mono prefix is dropped for the cation-like species, the one that's listed first. So for example, the commonly known compound carbon dioxide is not listed as monocarbon dioxide. That mono prefix for the first is dropped. Okay, so carbon dioxide means one carbon, two oxides, or two oxygens. So if the prefix ends with an A or an O, and the anion-like species name begins with a vowel, then the A or O on the prefix is dropped. Okay, so for example, back to carbon monoxide this side. So carbon monoxide, not carbon monoxide. So that vowel there is at the end of the prefix is dropped. Okay, so with these sort of naming conventions, please name these binary compounds. So pause the video and give it your best shot, and then we'll go through together. Okay, CO, we just talked about this one in our example. So there's one carbon, but we dropped the mono, so carbon is the less electronegative, oxygen's the more electronegative, so that comes second. Carbon monoxide. And we drop that O on mono to make it carbon monoxide. CO2. Okay, again, it's monocarbon, but we drop the mono, so carbon dioxide. All right, the next one, PCl3. All right, so the phosphorus is the more cation-like, the Cl3 is more anion-like. So that's going to be a monophosphorus, but again, we drop the mono, so it's called phosphorus. And then there's three chlorines, so we drop the INE ending, make it an ide, and so the three gives us tri, so phosphorus trichloride. Next one, SF4, is going to be one sulfur, so we just write that as sulfur, And then there's 4 fluorines, so that gets us tetrafluoride. Okay, finally, N2O4. So we have 2 nitrogen, so that gives us dinitrogen. And then 4 oxygens, that would give us not tetraoxide. You drop the A at the end, so that would be tetroxide. Okay. Next, write the chemical formula and the name for these compounds. And so the color coding is written down below the drawing. So pause your video and work through those. Okay, the first one here, we have our purple is phosphorus, and we have 1 of those. So we have phosphorus, and then we have chlorine. And so chlorine is going to be the more anion-like, so that's going to come second. So we have 1 phosphorus, and we have 1, 2, 3, 4, 5 chlorines. And so that's going to be named phosphorus. 5 means penta, so pentachloride. The next one here, we have 2 of our blue nitrogens, 1 of our red oxygen, and we know that the nitrogen is going to be more cation-like than the oxygen because there's a lower electronegativity. So that will be N2O, and that has the name dinitrogen monoxide. Okay, so rules for drawing Lewis structures. So we went over in the previous lecture some very basic Lewis dot structures. But as the molecules get to be more complex, we need to have a more comprehensive set of rules for drawing proper Lewis structures. So whenever you're drawing a Lewis structure for a molecule, I suggest that you follow each of these steps to a T. And so it's critical that you don't skip any of these steps. Okay, and so for the example for drawing this, we're going to use the nitrate ion, NO3 minus, as our example. Okay, step 1, valence electrons. So we need to find the total number of valence electrons for all of the atoms in the molecule. Okay, and then add 1 additional electron for each negative charge in an anion, or subtract 1 electron for each positive charge in a cation. Okay, so we have step 1, we have NO3 minus. So if we take a look on the periodic table, we see that nitrogen has 5 valence electrons, and then we have 3 individual oxygens which have 6. And then that negative charge is going to have us add 1. Okay, so when we plug and chug, put all these together, we have 24 total valence electrons. Step 2, connect the atoms. So draw lines to represent bonds between atoms and place the least electronegative atom as the central atom. Okay, so if we take a look here, nitrogen is our least electronegative atom. So we're going to place nitrogen in the middle. We're going to surround it by oxygens. And then we're going to draw lines, single lines here, to connect each of our atoms to the central atom. Okay, next. Step 3, assign electrons to the terminal atoms. So subtract the number of electrons used for bonding in the previous step from the total number determined in step 1, and then complete each terminal atom's octet except for hydrogen, which gets a duet. Okay, so we know that each of these covalent bonds consist of 2 electrons. So there are 2, 4, 6 electrons that we've already used in drawing these single covalent bonds. So if we subtract our 6 electrons from our valence, we have a remaining of 18 electrons remain. So now we start to assign those 18 electrons to our terminal atoms, which are the ones on the outside. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, so now we check to make sure each of these terminal atoms have their octet satisfied. And we can see again, this line stands for 2. So there's 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So we have the octet satisfied for each of these terminal atoms. And we used up all 18 electrons, so 0 now remain. Okay, that was step 3. Step 4, excuse me, assign electrons to the central atom. If unassigned electrons remain after step 3, place them on the central atom. So we can see we have no electrons remaining, so for step 4, we have nothing to do. Step 5, multiple bonds. If no unassigned electrons remain after step 3, but the central atom does not yet have an octet, use one or more lone pairs of electrons from a neighboring atom to form a multiple bond, either a double bond or a triple bond. Okay, so we take a look at our central atom here, and that has 2, 4, 6 electrons around it. So we do not have a complete octet, and we don't have any electrons remaining. So what that means is we have to take a lone pair off of one of the terminal atoms, and we bring that lone pair down. And so what that has the effect of doing is making this now a double bond. So now we have a double bond to that nitrogen, and we can slide these lone pairs just so they're a little more artistically represented. So now if we take a look again now to see if we have octets for all of the atoms. So 2, 4, 6, 8, 2, 4, 6, 8. So both of these bottom oxygens are good. The top oxygen, 2, 4, 6, 8, we're good. And this nitrogen in the middle, 2, 4, 6, 8. So we're good on all of the atoms now having octets assigned. That was step 5. Step 6, determine the formal charges. So determine the formal charge on each atom and choose the arrangement that minimizes the number of formal charges. So the overall charge on individual atoms must equal the charge on the entire compound. So negative charge should be on the most electronegative of atoms. So the formal charge is equal to the number of valence electrons for a free atom minus 1/2 the bonding electrons minus the number of non-bonding electrons. Okay, so this definition for formal charge seems like it could be a bit cumbersome and a bit difficult, but really I'll show you it's not. So we need to determine the formal charge for each individual atom. Excuse me. So for this oxygen first, we determine the number of valence electrons in the free atom. So for formal charge will equal, for this oxygen, we have 6 electrons that are valence electrons. We find that from the periodic table. Minus 1/2 times the number of bonding electrons. So we have 2 electrons for the one bond, 2 electrons for the other. So 1/2 of 4 total bonding electrons. Minus the number of non-bonding electrons, which is 1, 2, 3, 4. Okay, so the formal charge equals 6 minus 1/2 of 2 electrons is equal to 2 electrons. Or sorry, 1/2 of 4 electrons equal to 2, minus our non-bonding electrons, which is 4. So 6 minus 2 minus 4 gives us a formal charge equal to 0. Okay, so formal charge equal to 0. Okay, if we do the same thing down here, formal charge is equal to 6 valence minus 1/2 of our bonding electrons, which we have 2 here, minus our non-bonding, 1, 2, 3, 4, 5, 6. Okay, so we have a total formal charge here. 6 minus 1/2 of 2 is 1, minus 6. So that gives us a formal charge equal to minus 1. So we have a formal charge equal to minus 1 for that oxygen. This oxygen over here is exactly the same as the other one. So again, we'll have our formal charge equal to minus 1. Next we do for the nitrogen. So our nitrogen here, we have our formal charge is equal to our number of valence electrons on the table, which is 5, minus 1/2 the bonding electrons. So half, 2, 4, 6, 8. So half of 8 electrons, minus the number of non-bonding electrons, which we don't have any. So that's 0. So 5 minus half of 8, which is 4, is equal to +1. Okay? So the overall summation of all of the formal charges on all the atoms has to equal the overall charge on the molecule. So 0 plus 1 minus 1 minus 1 gives us an overall formal charge on the molecule equal to -1. And if we remember, we're making NO3 minus. So this all checks out. And so we see our negative formal charge is on our more electronegative atoms. Our positive formal charge is on our more positive atom. And if there's any other way to rearrange rearrange this atom in order to minimize the formal charge, that would be a more favorable conformation. Okay, but this is the best way to organize. So the final thing that we would like to do here, before we get to our resonant structures, the step 7, is we want to indicate that there's an overall charge on the molecule. So the way we do that is we put brackets around the entire molecule and we say there's an overall negative charge. Okay, and then we can also put our formal charges here, that there's a negative charge on this electron or on this atom, negative charge on that, and a positive charge on that. So that indicates our formal charge -1, -1, and +1, with an overall charge of minus. Okay, the last step is to list any resonant structures. So multiple Lewis structures can have the equal probability of existing at once. So we form that double bond here by moving a set of electrons from this top oxygen. But we could have done it for the bottom left or the bottom right. So what exists are what are called resonant structures, which are other different species that could occur if we would have drawn the species differently. So we have equal probability that we could have made that double bond with any of those 3 oxygens. Okay, so these 3 structures here are called resonance structures. Okay, that's it. Those are all the steps that you need to do in order to draw a proper Lewis structure. So this would be, with showing all of the resonance structures, would be the correct answer. All right, before we move on to the next thing, I want to quickly give you a little shortcut for calculating formal charge of each atom. So instead of the sort of convoluted equation of half the bonding electrons and half half the bonding electrons, my simplified equation is the formal charge is equal to the valence electrons minus the number of markings. Okay, so what I mean by that is we know that each of these covalent bonds here includes 2 electrons. But we only want to count one of the electrons. That's what 1/2 the number of bonding electrons means. So what we do is if we just count this single bond here as just 1, that's the same thing as saying 1/2 of 2. So what I would do for this one is number of valence electrons for oxygen is 6, minus the number of markings. 1, 2, 3, 4, 5, 6. 6 minus 6 is equal to 0. For this guy here, valence electron 6, minus number of markings, 1, 2, 3, 4, 5, 6, 7. 6 minus 7 is equal to -1. Same thing over here, -1. Here we have valence electrons for nitrogen is 5, minus number of markings is 1, 2, 3, 4. Equals +1. So it's just it's a shortcut, easy way for you to be able to quickly calculate formal charge. Okay, so this method for drawing Lewis structures works very well. But there's a few exceptions to our pre-established rules that we need to make sure that we lay down for you guys, um, so that your Lewis structures can actually reflect reality. So exceptions to the octet rule are there are several different, excuse me, there are several different exceptions to the octet rule. One of them is if you have an odd number of electrons. The next one would be for group 3 elements, especially boron. And the third one is called expanded octets. Okay, so I want to focus on the second two of them here. So for our boron group, so we know that boron has 3 valence electrons. And so if you form BH3, that will form 3 individual covalent bonds. In this case, there's only 6 electrons surrounding boron. But this is actually the energetically stable true arrangement for boron. So instead of being a complete octet, boron will be happy with just 6 electrons. The other one that I'd like to point out to you is the expanded octet. And so this can be present for any of the central atoms that are in the n equals 3 energy level or above. So we're talking about atoms such as phosphorus or sulfur or chlorine or bromine. Any of those atoms that are n equals 3 energy level or above can be exceptions to the octet rule, and where we have an expanded octet. And so what this expanded octet means is that these central atoms can actually accommodate more than 8 electrons. So for example, you can see a compound of PCl5 or PCl6. And in that case, once you work through your rules for drawing Lewis structures, you will find that these two orientations for PCl5 and PCl6 are the optimal orientations. And you can see here we have 10 electrons and 12 electrons respectively around those central phosphorus atoms. And so this is what's called an expanded octet. But it's very important to know that our N equals 2 energy level. So if we have a carbon or an oxygen as the central atom, or a nitrogen as the central atom, cannot have an expanded octet. It's only energy level 3 and above. Okay, with that, I'd like to invite you guys to work on the accompanying Lewis structure worksheet to go with this lecture, and you can let me know in class if we have any issues. All right, that's it for the day. Thank you.